Welcome. In today's video, we're going to be looking at maximum likelihood estimation for the rate parameter of the Poisson distribution. So to begin with, suppose we have a series of independent and identically distributed random variables, x1, x2, all the way through to xn, and we write IID on top of the sign there, or the distributed sign here, and suppose that they have a Poisson distribution, each of them with the same rate parameter lambda. Now, if this is the case, then the probability mass function, or the PMF, of each xi is given by this particular formula here. We write P of xi given lambda, so that of course is the parameter lambda, is given by e to the negative lambda, lambda to the xi over xi factorial. And of course this is for the case where xi is an element of 0, 1, 2, and so on and so forth. So it takes all the natural numbers, including 0. So what do we first have to do? Well, the first thing we have to do is compute the likelihood function. So the likelihood function is given by, well, what we do is we take all the parameters, well, there's only one parameter in this case, we're dealing with a single dimensional case, so we've got L, so L is the symbol for the likelihood, L of lambda is equal to, now the likelihood function is given by the product of all the respective marginals. So in this case, we have the product of xi's, the product of probability x equals xi from I equals 1 to n. And now what we do is we're going to, the product here, so what we've got is this particular function up here. We've got the Poisson PMF, so we're going to substitute that in. So that gives us I equals 1 to n e to the negative lambda, lambda to the xi over xi factorial. Now I'm going to do a bit of simplification here, not much, but enough. The first thing we're going to note is that it's all in product. So what we can, because it's all multiplied together, what we can do is we can actually individualize it. So, and when I say individualize, I mean, okay, product of these together, product of these together, and product of these together. So what do I mean there? We can write I equals 1 to n e to the negative lambda, I equals 1 to n lambda to the xi here, and that's all over product I equals 1 to n of xi factorial. Now, in this case, or in this scenario here, we have the product of I equals 1 to n of e to the negative lambda. There's actually no index in this expression here, so we're actually just multiplying itself n times. So that ends up giving us e to the negative n lambda. Now, the next section here, what we're doing is we're taking the product of lambda to the xi's. Now, the product of lambda to the xi's actually becomes, using our power laws, actually becomes lambda to the sum of I equals 1 to n of xi. And of course, the part down the bottom, the product, I'm just going to rewrite the same here. Alright, and don't forget the factorial. Alright, so we've derived our likelihood function. So now we have to find the log likelihood function. So the log likelihood function is So what is the definition of the log likelihood function? So I use a lowercase l to denote the log likelihood function. So L of lambda is given by log L of lambda. So in other words, it's the log of the likelihood, which obviously is implied by its name. So then what I'm going to do, I'm going to say that's log. I'm going to take my expression that I derived previously for the for the likelihood function above here. So that's going to give me e to the negative n lambda here. Lambda to the sum of I equals 1 to n xi all over I equals 1 to n xi factorial. Now we're going to continue here a little bit, and we're going to say, well, how do we simplify this? Well, we're going to use some of the log laws that we've encountered before, and remember, the log of a product is the sum of logs. We're going to use things like that. So here we've noticed that there's log e to the negative n lambda here. So first we're going to use the log laws. So that becomes e to the negative n lambda, plus log of this expression here, xi. And because the product of xi factorials is down the bottom, we actually have minus log sum of I equals 1 to n xi factorials. Now we can do a bit more simplification. Now, log e to the negative lambda here actually just simplifies down to negative n lambda, because you're taking log of an exponential, so you just need to look at what the power is. Now, log of something to the power, what happens? The power here comes down the front of the expression, so that becomes plus sum I equals 1 to n xi, and then we've still got log lambda, so we can think of that kind of in brackets. And then this expression here is not going to change much, although we could do some simplification here. I'm not going to. So now what we have to do in order to find the maximum likelihood estimate is we're going to have to take derivatives. So the derivatives with respect to lambda are, so we're going to take the first and second derivative. The first derivative we're going to take in order to solve for the maximum likelihood estimate. The second derivative we're going to use to prove that it is in fact a maximum. So we'll do that now. So we've got the delta log of the likelihood over delta lambda. So now we're just differentiating. So we've found the log likelihood. We're going to differentiate this expression here. So the differential of negative n lambda just becomes negative n. The differential of this expression, you can treat this as a constant in lambda, so it's like a constant at the front, but the derivative of log lambda is 1 on lambda. So you've got something like 1 on lambda sum I equals 1 to n xi here. And of course, there is no expression involving lambda here, and so when you differentiate this, it just simply becomes 0, so we leave it out. So now we're going to take the second derivative of the log likelihood function with respect to lambda. And then we notice now negative n just becomes 0 because there's no expression involving lambda. Now 1 on lambda when differentiated becomes negative 1 on lambda squared, and we've still got the sum I equals 1 to n xi kind of there as our constant. So still haven't completed this problem in any sense. We've still actually got to find an expression for the maximum likelihood estimate. So to find the maximum, or the MLE of lambda, and which we denote lambda hat, we solve the following expression. dl of lambda over d lambda evaluated at the maximum likelihood estimate is equal to 0. So now we're going to take our expression that we solved, or that we had above here. That expression is negative n, let me write it out. So if and only if negative n plus 1 on lambda, the sum of I equals 1 to n x I is equal to 0. Now what are we going to do here? We're going to move the n to the other side. So we've got 1 on lambda, I equals 1 to n x I equals n. And this leaves us with one final expression, one rearrangement. So what I'm going to do here is I'm going to multiply lambda on this side, and then I'm going to take the n to this side. So that actually leaves us, and I should have written some hats in here because we're evaluating at lambda hat. So this leaves us with lambda hat is equal to 1 on n, I equals 1 to n x I, and of course we know what this definition is, we know what this statistic is. It's actually defined as the sample mean, and so the sample mean, I give this expression here, a bar with, or a bar on top of the x, and with an n as the subscript to denote that there are n samples, or n samples. So now, the final step in this process, we've gone through the derivatives, we've derived the likelihood function, the log likelihood function, the derivatives, we've found the MLE. However, now we must prove that it is, in fact, the maximum likelihood estimate. And so, to prove, I'll do it in the next line, to prove that the log, or the likelihood function slash the log likelihood function is maximized at lambda is equal to lambda hat, we must show that the second derivative of the log likelihood function with respect to the parameter evaluated at the MLE is less than 0. In other words, we have to show a negative second derivative. So note that, so where was our second derivative? That's why we found it before. So here is our second derivative here. So I'm going to just copy and paste, or copy this particular paste. So the second derivative, well, let's take a closer look here. The second derivative, remember xi, the sum of xi's, well, the xi's, remember xi can only take values 0, 1, 2, and so on and so forth. So the sum of the xi's, the possible values, or the observed possible values, all of these have to be greater, or the sum of these has to at least be greater than 0. Technically, it could be greater than or equal to 0, but that wouldn't be a very interesting sample. So I'm going to assume at least one of them is greater than or equal to 0. Now, if I just focus on 1 on lambda squared, well, lambda squared is definitely a positive number because anything squared, negative or positive squared, is positive. 1 over a positive number is still positive. So together, this expression here is also greater than 0. So you've got a number greater than 0, a number times a number greater than 0, with a negative out the front. Now what does this tell you? Well, this tells you that altogether, that this is less than 0 for all lambda. For all lambda, an element of, and I'll say 0 to infinity, because the Poisson parameter can only be a positive number, positive real number, I should say. And so automatically we've proven that if it's going to be less than 0, no matter the value of lambda, then also evaluated at the MLE, it will also be less than 0. And so now this tells us that therefore the maximum likelihood estimate of lambda is in fact lambda hat is equal to the sample mean. And you notice here now, instead of writing it as the observations, I've written it as a random variable. I've capitalized it. And this concludes our video on how to find the MLE for the rate parameter of the Poisson distribution.